Alright, welcome to this video for Chem 161. We'll continue looking at some content for Chapter 4, touching on ideas of resonance and how to handle polyatomic ions. Okay. So let's introduce the concept of resonance by tackling a Lewis structure example, and we'll look at O3, the ozone molecule. Okay, so if you're applying your steps for drawing Lewis structures, you'll see that we have oxygen in group 6, so 6 valence electrons. We have 3 of them, so we have to make it a Lewis structure with 18 valence electrons. Okay, there are 3 oxygen atoms in this molecule, so it doesn't matter which one goes in the center. We'll put one of them there, tether an oxygen molecule flanking to the left and one to the right. I've just used 4 valence electrons, so I'm now down to 14 valence electrons remaining. We distribute to the periphery atoms, starting with the most electronegative. Oxygen and oxygen are the same, of course, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We've just used 12. We have 2 remaining. We've got octets at right, octets at left. Take a look at the central oxygen atom, only 4 electrons there, so we clearly have to apply our last 2 electrons to that central oxygen. And now we've used all of our valence electrons for this ozone structure. And now we are now at step where we consider borrowing pairs of electrons to reach that octet. Okay, so this is step 5. So it doesn't matter which one we choose. We've got oxygen at right, at left. So we've got to consider doing a borrow. So when we do this, the result will be 50-50 chance that some of you would have chosen the option at right, the other would have chosen the option at left. And we'll see that both are correct in that if we simply borrow a pair of electrons here to establish a double bond, we have the option of double bond at left as such. And if you ran your formal charges, you would see that this is formal charge -1, and this is formal charge +1. And overall, the molecule is neutral. These formal charges added up, and that's what we see reflected in the formula. So that is one plausible Lewis structure. The other, of course, is had we chosen to do the opposite. So what if we had chosen to borrow a pair at left instead of this? Well, that option would have looked like this. Essentially the mirror image of what we have above. And as you can see, that is equally plausible. So we call these two fully valid and correct Lewis structures. We call them plausible Lewis structures. They're both correct. And this establishes the idea that we have both as contributing to the overall structure of the molecule. So we call this resonance. So these two structures coexist with one another. And so we actually list them both as the answer for the Lewis structure of ozone. They're both correct. And we have the idea that the double bond that we've created is actually moving from one position to the next. Okay? And so that double bond in short is kind of jumping from one spot to another to help us with that idea. Okay, so you see that there. To actually show that, you can kind of think about what the electrons might be doing there. And so I'll show that here, where we're establishing this double bond, and that double bond is kicking out to the rightmost oxygen atom, and we see those new electrons atop. And this can reverse itself. Those electrons can kick back in, reestablish a double bond, and this can come back. So this double bond is moving across 2 different sites. And so then we have the idea of this double bond actually looking like it's more of a 1.5 bond at each spot. Okay, so we could actually show that with a bond order calculation that your textbook introduces for you. Okay. So this is the idea of resonance. Okay, so we'll just clean this up so we can get some notes for resonance here. Knowing that we have two correct structures that are valid for the ozone molecule. And resonance occurs when a molecule can be represented by two or more plausible Lewis structures that differ only by the distribution of electrons, and the true structure is a hybrid. So we've reflected that in this example of ozone. These are called resonance structures. So we've drawn two resonance structures here. They're separated with a double-headed arrow to mean that they're in balance with one another. And we see that the electrons in the resonant hybrids are spread over several atoms. Okay, so that is to say the double bond is delocalized between two spots. This actually puts more double bond characteristic at the neighboring position, helps strengthen that bond, and we end up with more stability. Okay, so that the resonance structures impart stability to the molecule. Okay, good. So we'll take a look now at this idea of polyatomic ions as well. So rule 6, we haven't necessarily had to apply if you're watching these videos in order, where we have to apply brackets and indicate charge. So let's take a look at the example of Nh4 Plus to tackle that option. Okay, so Nh4 Plus, we have nitrogen from the 5th column in the periodic table. So we have 5 valence electrons from that nitrogen. We have hydrogen giving us 4, so we're going to have 4 times 1 valence electrons there. And importantly, we have a positive charge. Okay, so how do we account for the positive charge? Well, to result in a positive charge, we have to remove an electron. So we're going to actually do a -1 valence electron in our total here to handle this. So we're going to have 4 plus 5, that's 9 valence electrons. Take away 1, we've got 8 valence electrons to work with in this Lewis structure for the ammonium plus ion. Okay, so the rest is fairly straightforward. Nitrogen in the middle. We'll decorate the skeleton with hydrogens in each position tethered by 2 electron covalent bonds. This is our skeleton structure. We've just used 8 electrons for this. We have no more valence electrons to work with for the structure. Each hydrogen has a duet. That is good. The nitrogen also sees an octet, so that is good. So all atoms are seeing an environment that is aligned with the noble gas column 8 that we have from the periodic table. So thus far this is good. Our last job is to check formal charges. So if you did this on each hydrogen, you would find formal charge of 1 at each hydrogen, of 0 at each hydrogen. And if you did a formal charge on this nitrogen, you would see that the formal charge is equal to +1. Okay, so this is already a hint that we need to do more respecting rule number 6. Okay, so what that looks like is we're reminding ourselves that we're dealing with a polyatomic ion. When we've handled this in balancing of formulas for ionic compounds, we've used parentheses to reflect the overall balance of these in the formula. And we do something similar, if you want, in Lewis structures, except we're going to use big square brackets. And we're going to reflect that this charge exists across the whole polyatomic. So we're going to put that positive charge right there. So there we've just designated charge, and we've used brackets for this. This is the correct structure, Lewis structure, for the ammonium cation Nh4 Plus. Okay. All right, we'll tackle one more in the carbonate polyatomic, and we'll actually see something interesting that arises from this. So the example is CO3 2-. Okay, carbon, 4 valence electrons, 3 oxygen atoms, so that's going to be 18 valence electrons, and then we've got -2, so the 2- piece means we have to have 2 valence electrons additional. Okay, so this Lewis structure has to be built with 24 valence electrons. Okay, least electronegative element in the middle, carbon. More electronegative elements, oxygen at the periphery. Okay, 1, 2, 3 oxygen atoms there. Our valence, our skeleton has just used 6 valence electrons, so we're now down to 18. We can now decorate the periphery atoms. 12. And there's our 18 valence electrons. Okay, so our skeleton now has all valence electrons applied, and now we have to consider borrowing. Okay, so at this point, hopefully some ideas for resonance are kicking in that we've got the option to borrow from the left, borrow from the right, or borrow from the bottom to bring in a double bond into this structure to help us. Okay, so for example, if we were to borrow this pair, we would establish a double bond. That would end up looking like this structure here. We would find that we have formal charge here of -1, formal charge here of -1, formal charge here of 0, and a formal charge here of 0. No two alike charges are directly neighboring each other, that's okay. We know that the overall structure must be overall 2-, so we have to put our brackets and indicate that charge. And this is the correct Lewis structure, a correct Lewis structure. And so we'll just kind of make room for those final details, brackets and the parentheses. We saw that the formal charge totaled up to -2, so we'll see that reflected in the final answer here. Big square brackets, 2-. Okay, so that is one plausible Lewis structure. Now, hopefully you recognize that there are a couple of other options here. We could have that double bond exist across a couple other spots. So to show that how that double bond would shift, we can imagine one of the lone pairs pushing into a double bond position. If we don't do anything on the other double bond, we would exceed the octet on the carbon, so we've got to restore double bond there, and this would give rise to our next plausible Lewis structure, which is going to be carbon, single bond to that rightmost oxygen. We have a double bond down below now. And we have the remaining untouched oxygen at left. Square brackets, the overall structure is still 2-, and that is an equal and correct additional Lewis structure here. Okay, as you might expect, we could also push a double bond out onto the right position. So we can imagine this giving us a double bond. We need to do something on that carbon, otherwise it has too many electrons, and so we'll do this to give us our last and final Lewis structure. And so this will look like an oxygen double bond at left to the carbon, now a single bond to the oxygen down below, and likewise a single oxygen to the right. Okay, and that's 2- as well. So there's 3 resonance structures for the carbonate polyatomic ion, CO3 2-, and they are all in balance with one another, contributing to the structure, spreading the double bond over 3 centers, imparting stability, and they are all in balance with one another, shifting constantly. So this is how we show the 3 correct Lewis structures for the carbonate ion, and it's nice to show them without sort of the ideas that led to our work to create them, so I'm erasing those arrows. Those would be the 3 correct answers for the Lewis structure for the polyatomic carbonate anion. Okay, so the simple exercise of creating a Lewis structure can actually be quite laborious. You may have to actually list more than one correct structure and show these resonant arrows, showing that they're in balance with one another. Okay, so we've touched on the ideas of resonance in neutral molecules. Ozone, as an example, gave us 2 Lewis structures. This is the correct answer here for that. We can also see resonance in polyatomic ions. So we saw that in the carbonate option, and in the former example of ammonium, there was no resonance, and we better clearly identified our first steps using brackets and denoting charge on a Lewis structure. Okay, please email if you have any difficulties with